Hi everyone. I think this is on here. My name is April, and I'm going to talk a little bit about reproducibility. I'm going to focus on a little bit of data management stuff, but also just sort of those discrete best practices that you apply to your data and your code at any point in their workflow to make it a little bit more reproducible. I'm focusing on computational reproducibility. So the link to the slide deck is right there. I recommend you follow along because we'll have some links in there to dive into the exercises, and it's easier to just click on them than to try and type them in. Right. So generally speaking, we're going to talk about organization, documentation, automation, and dissemination of research as those things relate to computational reproducibility. Because we're only here for a few hours, I'm going to provide a lot of resources that I've curated that are my favorites that are good to get started with in the slide deck, which we won't spend a lot of time in detail with, but you can go back to and hopefully have a sense of how they might be useful for you. And hopefully we'll be able to get our hands wet a little bit with trying out how to take a bunch of research materials and make them reproducible so that you can share them with people outside your lab or collaborators, or even find them again a few years later and remember what you did and get things started again. So generally speaking, we're going to do a little bit of hands-on stuff. We're going to not talk too much about theory, but there will be resources in the slide deck if you want to dive deeper in any of the areas we're going to talk about. And feel free to interrupt me with questions along the way. It's meant to be adaptable enough where if you have certain things that apply to your research that you want to go on a tangent about for a little bit, we can do that. Okay? So generally speaking, we're going to talk about what we mean by computational reproducibility. We're going to talk about organization, do a few exercises in how to organize your directory or repository to make it a bit more reproducible. We're going to talk about some of the basic minimal documentation you would provide to a project so that someone else can understand what you did and get started with reusing it and building upon it. We're going to talk a bit about automation and then finally dissemination of your data and code. But first, let's ask you guys some questions. So, raise your hand if you think that there is a reproducibility crisis, a significant one in your fields. Anybody? Okay, there's a few people. Raise your hand if you think there's like maybe a problem, but it's not a significant crisis. Okay, a few people. Raise your hand if you don't know. There's always some people that are like, I wish I knew that was an option from the beginning. And now raise your hand if you think that there isn't a crisis. There's usually one person in the room, but okay, we're all on the same page here. This is an issue that, generally speaking, across the research community we're concerned about. The disagreement comes down to, what are the solutions, how serious is the problem, and that sort of side of the conversation. But we're kind of on the same page that the way that we did things in the past, now that we've reflected upon it and understood a little bit more about the effects of those practices, we realize that there's some things that need to change in order for our published literature to be more reliable, more robust, and more reproducible. But the way I like to frame it is more about our own work, our own collaboration than our own efficiency. So raise your hand if you've ever failed to reproduce an experiment by someone else. So a colleague, say maybe you tried to reproduce a method that was in a paper or something like that. Anyone have a hard time doing that in the past? Yeah. Now, raise your hand if you've ever had a hard time getting your own work to be repeated in your own lab a few weeks, months, years down the line. Okay. So a lot of these things that we can adopt into our own research workflow to improve reproducibility, they overlap with those things that will actually make it easier for ourselves to understand what we did a few weeks, months, or years down the line, and also those things that will make it more easy for someone in your lab to pick up your work if you move on to another position or decide to work on a different project. So I like to frame the types of practices that we're talking about today as practices that will benefit you first. You are your most likely collaborator. Your future self is the person that you are documenting for. So when you see a big list of best practices and you're trying to decide which of these things you're going to adopt into your own workflow, pick those things that you know are your own trouble spots for your own workflow first. And that will help you improve the efficiency of your work, at the same time nudging your work down the spectrum of reproducibility. So I like to think about this so-called crisis in reproducibility as more of an opportunity. So we have new knowledge, we've actually studied research for the first time, evaluated its robustness and ability to reproduce it, and we found that it's fallen short of what we'd like. So we have new knowledge that we can act on. And just like any discovery in the past, this discovery is an opportunity for us to do better. We also have new technologies. So we now have tools that can make it easier for us to improve how we document and organize and disseminate our work. So if we take some of these practices, incorporate them into our own work, then we have the opportunity to accelerate the knowledge building that we are hoping to accelerate. Any questions about anything so far? So we're going to focus on computational reproducibility. And this is a quote from some of the originators of the idea of reproducibility. And they framed these published articles that we're all working on in our own research groups as not the research itself, but an advertisement of the research. So when we publish a paper, it's a description of what we did, but it's not sufficient for someone else to actually understand all the nitty-gritty of the methods that we use. And now that most research is quite computationally intensive, at least using software at some point in their research, then leaving out that part of the methods means that someone that comes to your research is missing a big section of the method. So we can think about the fact that we're introducing more software and more code into our work as a part of the methods that need to be reported, and there's a lag between how we've traditionally shared our methods and how we need to be sharing them now that we're so reliant on software and code. So we need to be sharing our code, we need to be reporting and documenting the computational side of our work, because it can't be reproduced without that information. So one of the greatest barriers to reproducible research is this missing methods and missing code. There's a lot of other things that we should also have on our radar, but this is a nice discrete thing that we can tackle ourselves. So we're currently living in what I call the golden age of computational reproducible guidance. There's a lot of papers out there with a lot of differing sort of philosophies and stances on what is the most important thing to tackle in your work to ensure that someone else can rerun your data and your code and come up with the same figures, the same numbers, the same tables as you originally published in your paper, for example. Two of my favorite are these 10 simple rules for reproducible computational research, because it's 10 simple rules, so you can get started with them no matter where you're at in terms of your research. And there's also the good enough practices in scientific computing. So a lot of the stuff that I'm going to talk about today, many people would categorize as good enough practices, and I think that's appropriate for a course that's introducing you to some of these ideas. But as you start to adopt some of them, you'll find some people that will tell you how to do some of these things even better, to enrich better documentation and share better documentation. But when you're just getting started, focus on those like little things you can add to document what you did in a way that's understandable to someone outside of your research group. But one thing that you'll find when you're reviewing like these piles of guidance on computational reproducibility is that these four facets of reproducibility that I've framed this session to cover, they will come up in every single one of those. and that's the importance of reproducible organization, documentation, automation of your analysis, and dissemination of all your materials. I was supposed to click that through. So any of the steps that we go through today, you can take those of which are most useful to you in the short term, adopt them first, and every effort that you take to make your research more reproducible will benefit yourself in the future. And it will also nudge you down the spectrum of reproducibility. It's important to keep in mind that any of the practices that you adopt, it's not an all or nothing situation. It's not either your work is reproducible or it is not. You can always add a little bit more documentation, make the ease of reuse a little bit simpler for someone coming to your work for the first time. Even if you change one step in your next project, you are moving in the right direction. So all of the things that I'm going to talk about today are things you can apply to any part of the research workflow, but they are appropriate for also the very end. And the reason I do this is because in the past when I ran reproducibility sessions, I was introducing people to best practices that they needed to adopt at the beginning of their research. But of course I was meeting people who were in the middle of their research. So we're going to focus on those things that you can apply anywhere, including if you're just about to graduate and you haven't done any of this throughout your whole workflow, and you need to sort of do some, emergency documentation work to your work at the publication stage. These are things that you can apply to that work even then. So you'll notice that I left 2 sticky notes at everyone's table. Raise your hand if you've ever been to a software carpentry, or data carpentry workshop. No? Okay. So I highly recommend, if you are interested in learning a little bit more about scientific programming, they're great workshops. They're usually 2 days, and they teach you sort of a boot camp style of getting started with coding. But one of the things that they do really well is this communication system for groups of people working through technical exercises. So what we're going to do is at the beginning of every exercise, we'll put a pink sticky up on your laptop. And then when you've either finished it, or you're just like, I understand, I don't have any questions, then you'll switch it to green. Okay? Sounds good. Okay, we're going to start with something fun. We're going to create a little bit of data so that while we get through the documentation side of things, you'll actually know what it is you're documenting. So this is going to be fairly quick. We're going to, is everyone in the slide deck? Is there anyone that's still not in there? Okay, so we're going to click on this Google form here. And you should see something like this. So everyone put up your pink sticky. So what you're going to do is you're going to put your name in here. You're going to put, this is pre-trade, so this is trade number 0. And you're going to look at the candy selection that you have in front of you. It's pretty meager. But assess your happiness with that selection of candy. So if it's flavors that you like, you can pick higher. If you're don't like candy, you can rate it lower. Once you've put in some happiness rating for your candy, then click submit, and then switch your pinky to your sticky to green when you're done. So the link to the slide deck is right here. And it is on slide, what slide is this? Can someone see what slide number it is? Anyways, it says exercise 1.
Slide 19.
19. All right, so 1. Have you been able to find? Okay, we're not going to leave you behind. I'm going to check in on you in a minute. But most of you are here, so let's go on to the next. We're going to find one trading partner, and you're going to trade the candy you don't like for the candy that you do like. Okay? And then you're going to re-enter your new happiness rating with your new selection of candy at that point. So click on the Google form again. Put up your pink sticky. You're going to be doing a lot of that. There'll be lots of switching of the stickies. So trade with one person to see if you can get some better candy, and then resubmit your new happiness. And when you're done that, switch to green. Any questions? Is this confusing to anyone? You also have permission to steal candy from the NPCs next to you. That kind of improves the selection of candy.
Oh, that makes it better.
Normally I'd like to have a variety of candy, but this is what was available to me as I got up in Subway on the way here. Okay, so once you have resubmitted your new happiness with your selection of candy, this is tray number 1. You put in your name, tray number 1, your new happiness, then switch to green when you're done. Okay. And now the final one. So this is free trade. You guys are now welcome to trade with anyone in the room to improve your selection of candy. So put up your pink sticky. This will be trade number 2. So once you've traded with anyone you want in the room and you're satisfied with your selection of candy, hit submit, and then you can eat your candy.
There's also
Are you happy with that selection? Yeah. What's your favorite flavor? You don't like all of them. Okay. For those that came in and haven't, done any candy trade, don't worry. They're not learning anything right now. We'll just use this data as part of our documentation so that we know actually what happened in the room, and we can actually create the README files and data dictionaries that are appropriate for this fairly straightforward data set. Okay. So still a couple of pink stickies up, right? Perfect. Okay, so what's important to keep in mind when you're thinking about reproducible organization? One of the takeaways is the importance of centralizing your research so that you can keep track of all of your related materials, so that you can adopt version control, and so that you can back up all of your data. So one of the ways you can do this is by creating one repository or one directory that holds all of your research materials together in one place. Another thing that should consider is how you structure that directory. So it should be structured in a way that makes sense for your research and separate files from one another that are similar. So many times people will recommend that you separate, for example, your data in one subdirectory from your code in another subdirectory. But how that actually looks will relate a little bit to what types of materials are important for your research. And then the third thing that is not possible for everybody's research, but if it is, it's a good practice to get into, is to actually have a subdirectory called results or something like that, where you will explicitly save your figures, your tables, all of your outputs that are important to you as a direct function of your data on your code. So this keeps a connection living between the code that you're running on your data and the data that the most recent versions will save into the results file, so that when you look at those tables and those figures in that folder, you will know that that is the result of the most recent version of your data and your code. So the most basic subdirectory structure for reproducibility will have a data subdirectory, a code subdirectory, and a results subdirectory. But as with everything that we're going to talk about today, the important lesson is to have things structured in a way that makes sense for your research and gives people a little bit of information of what they'll find in each subdirectory and how those materials might relate to one another. So for example, there's different, if you start to look into case studies and repositories of people's research, you will see they'll have things structured a little bit differently. But just having those subdirectories labeled is a bit of extra information about what you're going to find in that repository and how to get started with reusing and building upon that. So there's lots of different tools you can use to help you stay organized. The Open Science Framework is free and it's open source, and it's a collaborative project organizations tool. GitHub is a good place for collaborative coding. And electronic lab notebooks. Raise your hand if you use an electronic lab notebook in your work. Anybody? Okay, there's one person that does. If you want to stay organized, there might be an electronic lab notebook out there that will make it easier to keep track of the experiments that you run. If you are thinking of adopting one, Harvard has put together this features matrix that makes it really easy to compare different platforms to one another. So depending on what functions are important to you, you can get a sense of how they compare to other platforms. So we've talked about why publishing a paper is really just the advertisement of your work. And so the obvious thought that follows that is that we need to share our code and our methods alongside our papers. But the step beyond that is it enough to just share our code and our methods? Are people able to actually get our code up and running again if we just share, say, our code or maybe a Jupyter notebook? Raise your hand if you've heard of a Jupyter notebook before. Okay, good, great. So this particular study, it's an informal study. It was sort of a little project put together by some friends at Open Data Day last year. They decided that they were going to sort of assess the reproducibility of the published literature, and the way they decided to do this was to identify papers that had been published in PMC that had some sort of Jupyter notebook accompanying them. So generally speaking, for those that aren't familiar with Jupyter notebooks, it's a type of what's called literate programming, which just means that you're actually knitting together your analysis narrative with the analysis itself. So you're not only able to see what someone did, but you're able to explain using a markdown language, for example, why you're doing a particular step. So it makes things both machine readable and human readable, which is nice. So a lot of people that are using this are using it because it provides some benefits for reproducibility, right? Because it's a little bit of extra documentation. So they were thinking it was going to be fairly straightforward to reproduce these papers. So they identified 107 papers, and they started to try and rerun those Jupyter notebooks themselves. And after trying, I think it was 30 or 32, they gave up because they were only able to actually get one running themselves. So they described this experience as hopelessly naive. They thought that it was going to be fairly straightforward because everyone says, if you share your code, you share your data, your work is not reproducible. And it is true that it is pushed down that spectrum of reproducibility. But what I want us to be able to do today together is fill in some of those gaps that they found in this study to ensure that we are not as naive and we are actually sharing things in a way that is not only theoretically reproducible, but actually will help somebody else easily get your code, run and understand your data themselves. So what did they find? They found that the files, the data, and the dependencies that they needed to execute the analysis were often missing from the paper. So people would be sharing a link to say just the notebook file or just the code file. So there's a bunch of things that our analyses are reliant on, and these things are called dependencies. It can be code, it can be other types of files. So what we can do is to organize for reproducibility. So we talked a little bit about how we can centralize things, so that's one way of organizing for reproducibility. Another thing to think about is what is the version of your code and your data that support a particular piece of research that you're sharing, either through a publication or with a colleague. You want to archive the exact version of your code and data and materials that were used to support that output that you're sharing. And you want to include those in your repository, so everything is there together, and there's a particular version that is marked, so someone can know this is the version that relates to this publication, and maybe this is the version to a follow-up publication you might make. Whenever possible, you should bundle all your dependencies together. It's not always possible. Sometimes people will have to go somewhere else to get some piece of software or some material that you can't actually store in a repository that you share, but it's something to aim for. And when people do have to go and sort of find these things themselves, you should provide enough documentation in your repository for them to have a sense of where to get it, how to get it, and what you did to get those materials, so that they have a sense of what type of work they will need to do to get it running themselves. And so then the core of that is, once you've archived the versions, you've put everything you can in one place, to link to that repository rather than just to the code file or just the data file. Does that make sense? Okay, so exercise 2. We're going to create one repository that holds all our related research files together, including our data, our code, our notebooks, our documentation, etc. So on this link, you will see there's a link to a GitHub repo. This is my GitHub repo. So everyone put your pink sticky up. So I expect that this will take a little bit of time to get going. But you'll see here a launch binder link. This is simply a way of taking a GitHub repository and spinning it up into what's called a container. Raise your hand if you've heard of a container technology, like Docker, maybe? Okay. So you don't really need to understand exactly what the magic is, but what containers allow you to do is to make your analysis portable from one computational environment to another. And they do that by creating sort of an isolated place that contains all your dependencies, like your packages, for example, and your any sort of configurations like that. You can put those into a container so that someone else can rerun your analysis without installing any of those things themselves. So it's a sort of an isolated environment that makes your research code portable. It's commonly used in the software development world now to make software portable from one environment to another. So Binder simply allows you to do that with the GitHub repo. So click Launch Binder. You're going to see this spinning thing. Once this turns to like a different view, I can't show you that view because I don't have it yet, but we're going to switch to a green screen, okay? Oh, I should have put the data up. Oh. Has anyone got anything yet on their screen? You got something? Okay, good. Oh. This is one of the things that I sometimes don't think about when I'm using someone else's computer. I'm not signed into my GitHub, so I can't actually update the data that we created together. But let it be known that this data that is in the GitHub is created using the same methods that we did together. So you do have a sense of what this data means, and I apologize for that oversight. I forgot to sign into my GitHub repo. Okay. So that simplifies things up. So we've got about 5 people that have gotten Binder to launch something. You as well? Okay. And then the rest of you are seeing this. Raise your hand if this is what you're seeing right now. Okay. Yeah, I knew this was going to be a little bit slow. It's always a cost benefit too, getting everyone to install something and troubleshoot that, or troubleshoot something taking a while to load. Here we go. So this is what I see. There's still some people waiting, right?
That's a question about where. So where does it all run? Where's it live?
Where does it live?
Yeah.
They have their own server. My Binder has a server that's free for anyone to use. You can run one locally if you want to. But yeah, it's I don't know where the server is actually located.
And the environment is set up, it's the same every time.
Yeah. So you put in, if you're interested in learning more about Binder, it's you need to put in a requirements.txt file, which we'll be talking about that. One of our exercises will be how to create a requirements.txt file. But that is a machine-readable documentation of all your dependencies. And Binder uses, it's called, I think, repo to Docker to spin up a container. So you can play around with anyone's code without installing anything locally. Okay, so there's a few people still waiting for this to appear. Is that correct? Are any of those that are waiting using Internet Explorer? No? It's just taking a while? Okay, well, I'm going to go ahead and demo things, and I'll check in with you guys once we get into an exercise and make sure that we've been able to solve this. There's a possibility that because this is at a server, it might, we might work through some things and crash and have to do it again. But the point is that we can go through together how to adopt these practices without having to install anything. So there's a cost benefit to that. Okay, so if you are here, what I want you to do is go up to the URL up here at the top. See where it ends with tree? Delete tree and put lab. And then hit enter. So what this is going to launch is called Jupyter Lab, which is simply a way of organizing your files. And it's designed by the same team that built Jupyter, so it works really well for Jupyter, but you don't have to be using Jupyter to use this. And for our exercises, it just makes it really simple. You can see here, this is my repository, everything's flat, right? It's all in one place, it's not organized in any particular way, but it is all centralized. So everything that someone needs to rerun my analysis is here in this repository. Okay, so there's a few people that are still waiting to, those pink stickies that are up right now, you're still waiting for, oh no. Okay, so everybody now is seeing this. Okay, well that's awesome. Okay, so we've created one repository that holds all our related files together, and you can see here I have a Jupyter notebook, I have my protocol here that explains exactly how I ran my experiment. I've got my data, I've got my code, I've got requirements.txt, which we'll talk about. So we'll go through all of the sort of components of this repository as we move through the session. But generally speaking, this is everything that someone needs to rerun my analysis and understand my code or understand my data in context of the analysis that are being run on it. This was just in case Binder didn't want to put videos in here, so you could go back to look at those later if you want. So the next exercise is to organize our research in a way that separates our code from our data. When you apply this to your own research, you will think about separating it in a way that makes sense for you. So this is an example on the right of one recommended structure for a directory for research. This is from Carl Broman, who writes a series of blog posts on reproducibility and data management. And this is how he personally prefers to organize his research. So you can find lots of examples of how to structure your subdirectory. But we're going to separate our code from our data from our results. So everyone put your pink sticky up. So we're going to create some folders. We're going to create, see this plus folder, new folder up here? We're going to click that. And we're going to rename it code. So then we can take everything that's related to our analyses. So in this case, we've got a Jupyter notebook. What is it? Control to do multiple things. Yeah. We've got 2 Python scripts. And then we've got a run.sh, which is a shell script, which is also called a master script in this case. And I'll talk about the importance of that for reproducibility a little bit later, but just to give you a heads up and a peek into why that's here, this is a script that runs all of our scripts from start to finish in order. So someone who comes to maybe a code repository for the first time and they see 10 different Python scripts, they might not know what order they need to be run in. And it's not uncommon for the order that a script is run in to affect the output. And in some cases, your analyses just won't work at all if you run in the wrong order. So let's drag that into the code. So once you've made a code folder and moved the code files in there, switch your sticky to green. Any predictions as to what we're going to do next?
Data folder?
Data folder. Okay, so make a new folder. We're going to call it data. And then drag your data file in there. So everyone put up your pink sticky. And once you've created a code folder and a data folder, switch it to green. I should have told you to put pink at the beginning. Okay. Okay, one more test. Who knows what the third folder is going to be?
Results.
Results. So everyone put up your big sticky. And if you have now 3 folders, oh, I've forgotten something. This is my code book for my data. So it's also known as a data dictionary. So this is going to go in data folder. So once your repository looks like this, switch to green. So just to give you a sense of why this matters, if you look at someone's repository like this, and you see everything organized just flat, you know, for a repository of this size, you can probably figure out what different things are. When you download it, you're going to have to sort through all these materials, open them up, and figure out how they relate to one another. So having things structured for people really helps them be able to reuse your work more easily. Okay. So the next important facet of reproducibility is documentation. So I already mentioned literate programming. That's one way of better documenting your analyses because it knits together your narrative so people understand why you are doing certain things and the context of your analysis, which makes it easier for them to dive in and reuse it. You also want to be sure that you document every element or variable in your data set. There's different ways to do that. We're going to talk about how to make a simple data dictionary or codebook, which is a bare minimum of something you can do when you're just about to publish, for example. But different disciplines have their own metadata standards, and it's probably a good idea if you have time to consult with either your library or some other colleague that has experience sharing data in your field to find out what those metadata standards are. If you find a discipline-specific repository for your data, for example, many disciplines have their own repositories for data, they will actually have a schema that they will recommend for the submission of your data. So that's actually the best practice. But the reason that I like to show people how to create a data dictionary is because it's appropriate for all data sets to have some type of documentation like this alongside it. And if you enrich it with extra metadata in your repository, that's a bonus. But at the very least, people should be able to understand what are each of these variables, what are each of these elements, what do they mean, what units do they use, how was that information gathered, how does it relate to other elements in the data set, are there natural thresholds? So for example, what are some natural thresholds for our data set? We have a happiness rating. What's the maximum happiness rating? Is anyone happier than 10 from this morning's exercise? So for someone coming upon this data set, if they didn't have a data dictionary, they wouldn't know what our max happiness was. And if they made an assumption of thinking it was something greater than 10, they might have think that we're just a bunch of very miserable people. So it's important to allow somebody to have a sense of how that data was created so that they don't accidentally misunderstand it, misuse it, or decide that they don't have enough information to build upon your work themselves. Another basic type of documentation to include in your repository is a project-level README file. So raise your hand if you've made a README file before. Okay, most. So the nice thing about a README file in terms of reproducibility is it's very adaptable. You can put a lot of different types of information into a project-level README file. It can include a file overview. It can include, some of the dependencies that your project is reliant upon. You can list those there in the README file. The reason why it's such a great place to provide that rich documentation for your project is for many repositories, this is actually the file that will be rendered when someone finds your work for the first time. So GitHub, for example, this is what they render. Many repositories will render the README file first. So you want to give credit, you want to have your contact information in there, you want to have citations to pieces of work that you used. The nice thing about a README file is that you can update it as your project evolves, and just updating the README file is a way of documenting the evolution of your project over time if you track that README with version control. And then finally, licensing. So we're going to, at the end of this, when we talk about dissemination, talk about how to choose a license for your data and how to choose a license for your code. But it is part of the documentation in the sense that what you're doing is telling the person who is coming upon your research repository how you wish them to reuse it. Are there limits to what they can do with it? Are there certain ways you'd like to be credited with this work, or are you going to make it openly available for anyone to do whatever they want? So licensing is how you communicate that. And if you share all your work and don't add a license to it, what ends up happening is people will just choose to not reuse it, even if it's useful for them, because they can't necessarily publish or wouldn't feel comfortable publishing the results that they might have achieved through using your data, even if you shared it publicly. Just sharing it doesn't mean that you've made it clear that it's open for reuse. I know you guys are going to be talking about version controls separately in another part of the class, so we won't go into that too much. But if you're using Python, raise your hand if you're using Python in your research. Anybody? And then the rest of you, what are you using? R. Yes. So if you want to use literate programming with R, the easiest thing to do is to use RStudio, and you can actually create R Markdown files or use what's called knitr, K-N-I-T-R, and that will create these very similar documents using R. And it's a great way of knitting together that analysis with the narrative. As I said before, these slides are meant to be resources. You can come back to them later if you want to dive into them a little more. There's a lot of examples of data dictionaries, README files, and licensing information. Another important form of documentation is the specification of your computational environment, as well as any packages or libraries that you're using alongside their versions. About 4 or 5 years ago, container technology first became used by researchers to help to not only specify that computational environment and those package versions, but to actually specify them in a way that would automate their reuse, so by containerizing those analyses. So I have that here under documentation just because it is sort of a natural progression beyond sharing this documentation in a way that is understandable by a human to having it be also understandable by a machine that can then rerun your code following that recipe. So Docker is the most commonly used technology in terms of sharing your code, and it's free and it's open source, and if you've got the technical chops, you can get started with just using Docker directly. Binder is another way of doing that. Wholetail is another way of doing that. There's a growing list of platforms available out there that you can use to more easily configure a container if you're not comfortable with using Docker directly. And so there's great resources that accompany these platforms. Binder has a great, this is what we're using here to run our exercises. It will explain all the different ways of documenting your dependencies so that Binder can spin up a container for you if you put your work into GitHub. Any questions so far?
Does it go to the dictionary you mentioned? Data dictionary?
Oh, you don't know what a data dictionary is? So data dictionary, and we're going to create one as one of the exercises, but it's essentially a type of documentation for your data set. So if you're working with data, so that someone understands what all of the names of each of your variables or your elements are, and all of that type of information in that context to exactly what those numbers mean, and that sort of thing. So we will talk about it in a little more detail. But it's an important part of the documentation. So what our friends that did that study with the Jupyter Notebooks found is that if you're sharing just a notebook, for example, or if you're sharing just your code, you're not directly expressing your dependencies. You might list them somewhere, but they're not actually included in that same document, so somebody has to still find a way to rebuild that, to rerun your code. And that seems like it shouldn't be too hard, but different versions of the same package can impact the output of that code, for example. So sometimes it will just break the code, and you might have a hard time getting it going. Sometimes you might have access to some of those libraries or that piece of software. It's best to try and contain all of those dependencies together and share them instead of sharing just the code or notebook itself. So one way of doing this is by publishing containers alongside of our publications. Container technology does allow you to directly express those dependencies in a way that allows someone else to just spin up a container, as I mentioned before, and that makes it portable from one person's system to another. So people can just dive in and get started with your work rather than trying to hunt down whichever version of ggplot2 that you used, for example. Okay, so we're going to talk about our run environments, our base environments that we might use, and then we're going to specify our packages and our dependencies with their versions. So let's go back into our Jupyter Lab and put your pink sticky up. Yep.
What's the difference between a container and like an executable?
And a what?
An executable.
Oh, and an executable. Well, I'm not actually very technically knowledgeable on things like that. I know that
Like the binaries that you would, if you need a new software, you just download and you can just download the binaries and there's no installation or anything.
yeah, so if you can do that and it provides the information in a transparent way, so people know not only, can not only get things running, but also can see the recipe, like can see the instructions, then that provides an extra benefit for transparency. But if your goal is simply reproducibility, just getting something up and running on its own, that sounds like it could be a good option for people because they wouldn't have to do the installation. But one of the things that's nice about Docker and these other container technologies is that you can have these, they're called Docker files, which is essentially a recipe for a computer to rebuild from scratch another container. And it does it in a way that is transparent because you can actually see, oh, first you load this, then you load that, and that sort of thing. So I guess I can't fully answer your question. I'm happy to look into it a little more and how to compare. But if your goal is to just get your analysis rerun and executables allow you to do that, then that does move you down the spectrum of reproducibility. But you probably should opt for things that are transparent whenever possible. Do you have any? Yeah.
I think my only concern about just having executables is, do you have access to the source code? Like, do you know what the code is, or is it all binary technique? So, I mean, from my perspective, it's just binary, and I don't really know what the code is. I don't know if I can trust it. So, but if it also comes along with source code, the source code, and you can recompile it.
Yeah, just for the sake of the video for people watching later, if you have access to the source code as well, then you have a sense of what it is that is being rebuilt and compiled. But if you don't have that, then you don't actually know what is being built without having that source code. Any other questions? Are you using executables now in your work?
Yes, always.
Yeah, always, yeah.
Well, if there's no executable, I've used so much different software, and it's really annoying to have to like build it every single time.
Yeah.
Because I'll run into all sorts of problems. I don't know what's the right version of another thing, and I just use the bin that it's a lot easier, and it's easier to just organize all the software.
Yeah. Yeah, and I think, like, generally speaking, part of the difficulty of talking about reproducibility across disciplines and across workflows is that the solutions are going to look different for different barriers, right? So if a particular discipline finds that sharing the source code alongside an executable is sufficient for them to like assess what someone did and also build upon it, then there's no arguing with that, right? It's an evolving field, and guidance is going to be best practices are necessarily going to be discipline specific, and many times like specific to the methods and barriers that you're going to run into. So I would say that as long as it provides enough transparency for your colleagues to feel like they can build upon that work, then that's an appropriate solution. And then as technology improves, you might find that there might be a more transparent solution available to your discipline, and then that can be the next best practice.
I'll just say one more thing. We're going to have a session on packaging and sharing. And in that session, there was going to be more discussion about how to package up your code so that you can share with other people. And the package there, I mean, we'll be talking about Common Core, which are executables, but it comes along with the repo so you can see the code. So a little bit more discussion.
Yeah, no, that sounds perfect. Yeah. That sounds like it would be perfect, like up your alley, the two things together. Okay. So I talked about the importance of documenting your dependencies. So here's an example of what that looks like. This is a requirements.txt file, which is essentially, each one of these is a package or a library in Python, plus the version of it. So this was created automatically, and I did that in this case, I used my shell script, and I just used pip freeze. This is going to, when I run it, save another version of it in results, but I wanted to have one in there so you could see what it looks like. But it essentially takes all of the dependencies that I have installed locally and creates a machine-readable and human-readable list of them. So this is good practice. As I talked about before, there's good enough practices, there's good practices, and then there's best practices. I would consider this a good practice because it does allow people to spin up a container if they wish to, but also just read it and manually install if that's how they prefer to do it. And the good enough practice we're going to talk about a little bit in when we get to the documentation section, but essentially if you don't have time to deal with these things and you put your dependencies listed in that human readable way here in your README file, it is not best practice. However, it does put you ahead of the game of a lot of people who are sharing their code right now, and at least in theory allows people to try and recreate what you did. And you can always come back to it later if you start to build on that work again and improve your documentation over time. So just because you don't feel like able to figure out how to create a requirements.txt file with this project that you're publishing maybe in the short term, doesn't mean that you can't still document that information for somebody and give them a head start in reusing your work. So that's how you would go about, it's not really an exercise, it's me showing you how you would put it in your code. You use either pip freeze code requirements.txt or condolist export code requirements.txt. If you're using R and you want a list of what packages you're using and what versions, you can use what's called session info. That's one way of doing it, and that will list all of your dependencies that you've used in your analysis. So again, I have the videos in there in case you ever want to go back to them. So the next step in documentation is the project level README file that I talked about before. So everyone has their pink stickies up still. I'm going to show you an example of a repository that includes all of the replication materials for a published paper. So the American Journal of Political Science requires that every author submit sufficient information for a third-party verifier to rerun all of their analysis, and will check that the numbers, the tables, the figures are the same as in their paper. And then they publish their repository alongside the paper. This is in a Dataverse repository, which is appropriate for lots of different disciplines. Raise your hand if you're using sensitive data of some sort. Okay, so a few of you are. Depending on how it is sensitive, there's different ways of sharing that data. Dataverse is starting to incorporate what they call data tags, which would mean that you could deposit your data into Dataverse, and people would only be able to access it themselves if they signed a data use agreement of some sort. So depending on how sensitive it is, that could be an appropriate way of sharing data. If it's clinical, there's a project at Yale called the YODA project, which is essentially a data broker. So you have a third party that's responsible for assessing data requests. These are considered experts in data, in sensitive data, and you can deposit your data to that type of brokered repository. And then when someone comes to your data set and decides that that might be useful for them, they can put in a request to use it, and they would have certain requirements that they would have to meet before actually being given access to the data. But you wouldn't be responsible for fielding those requests yourself, which is nice. There's a lot of, the barrier to sharing data is that you're worried about managing those requests. So that puts the responsibility on to a panel of experts, and then they can do things like check, what is the data being used for? What other data sets is it going to be pooled with? Will it be pooled with data sets that might violate people's privacy? So just because you have sensitive data doesn't mean you can't find some way of sharing it. But if it turns out that you can't share your full data set, sometimes you can share a subset of it that's been anonymized, for example, or at least a subset that allows somebody to understand the relationship between your final figure and the data itself. So you could have, for example, some places have simulated data that will allow you to you could play around with data that's the same structure and the same sort of statistical values as the real data to understand that relationship without actually being exposed to sensitive data itself. So there's lots of ways to share. If your data isn't sensitive, Dataverse is one appropriate place you can share it. Yep.
How large can the files be, the data files?
Oh, for Dataverse, I don't think they have a limit. I would have to check. Yeah.
But sometimes I have like databases of like 500 megabytes or 1 gigabyte.
Yeah.
I would imagine that's maybe too much.
It might be. I'm not sure. I know that there are data repositories that handle large data sets like without a problem, because that's the discipline-specific ones that have like large data sets in their fields. They just have to figure out how to do that. So if Dataverse can't do it, you can, I think it's called RE3. Yeah. So as you're trying to choose a repository for your data, re3data.org is a database of data repositories. You can search it by different criteria, and I'm not sure if size is one of those criteria, but it should be. But it could be a way that you can try and answer that question. So this is the replication data, but what I really wanted to show you is their project level README file. This is an example of a good enough, oh wow, it doesn't text right. Again, a problem with using a computer that is not mine. I wonder if I can open it with something else. Can I just read it? No. Okay, well, we'll abandon that for now. So you can go there yourself to the replication package and look at the README file. What I was hoping to show you, and you can look at it locally maybe to see this, at the bottom of their README file, they have a list of all their packages and their versions just listed there. So that is enough to get someone started. But for us, we have the beginnings of a README file here. So you have your big stickies up already. Let's go into our Jupyter Lab and double click on the readme.md. And then once you're there, we're going to do a little magic thing. We're going to left click on the README file and show Markdown preview. So this just allows you, as you're editing, to view what the actual rendered markdown file looks like. So this is the basics of a project level README that you want. You want some sort of informative title, for example. So here we can put candy swap of heading. Oops. You can start to fill in the gaps. So you'll see that a description is sort of like an abstract. You want to provide some context to someone who finds your repository for the first time about what this repository contains. So in this case, it's enough information, all the data and code needed to replicate the analysis for our candy swap. You want to provide the contact information, but the most important thing is this file overview. So this is where you can talk about what's in your data set. How does that data set relate to your code, for example? Do you have some code that runs on some data and some code that runs on other data? Otherwise, people only know that if they actually start to read your code. So, for example, your data files here, you would want to name data.csv is obviously not a really great name for a data file, but we would talk about what it is. It is the data gathered in we trade candy swap. Oops. And how it relates to other files. So the Python scripts and Jupyter Notebook refer to this. So you'll see here that this is like rather informal language. It's rather stream of consciousness right now. So depending on how much time you can refer to other README project README files in your discipline and look for the types of structure that they are using. But if you are about to publish and you're going to just throw a README file out there alongside your repository, it's okay to have things just explained in human language to make it understandable by someone else. And you can always update a version alongside a publication, update it again if you go back to your project later. The important thing is to provide some context and some instructions for getting someone started with reusing your work. So if there's any specific replication instructions that someone might need, this is a place you can put those. So there's specific challenges to specific work. This is a flexible enough place that you can put that information in here and someone will find it before they get started, before they come to those challenges while they try to reuse your work. Any questions about README file? So the other thing that we talked about was the Jupyter Notebook. So most of you are familiar with this already, so I'm not going to spend a lot of time on it, but for those who are new to it, this is what a Jupyter Notebook looks like. It is a mix of, in this case, it's markdown files, so this is where you write the narrative, and then, sorry, they're called cells, markdown cells and code cells, and you can sort of run those cell by cell, and it will create the output here, so it's all sort of together in one place. You can actually see not only what story you're telling about your analysis, but actually the code and the output all together. So you can hit either this run button, or I think it's Shift Enter. that work? Yeah. Will also run each cell. Any questions about Jupyter Notebooks? So we can update this here. Just by double clicking on it, I can change this to MSK. Cambridge. Okay, so if you checked out the README file, added a little bit to the markdown, if you don't have questions about the Jupyter Notebook,
Not questions, just all the code.
yeah, go for it.
Anyone knows what Jupyter stands for?
Ooh, you get extra candy if you do. Yeah,
Jupyter, Python, R.
almost.
Yeah.
Julia.
Almost, Julia.
Julia. Yeah, sorry, yeah.
I figured that was what was in your head.
You can actually, if you're working with R, you can use
That's true, yeah. You can use it with pretty much every open source language. And there's actually kernels available now for MATLAB.
Oh,
Yeah, I don't know how well they work, but there are ways of using it with almost any language. And it's, in my opinion, if you are getting started with programming, notebooks were really helpful for me because I was able to, this documentation of what I was doing was for myself. Understand, like, oh yeah, that's what that piece of code does. So if you are starting out with programming, it can be helpful. Any other questions? Yeah.
So here you're working with a flat file. Seriously, what if your data is in a MySQL or a database or complex image sets?
Yeah.
So how does this fit into all that?
So I think my general blanket answer to things like that is to start from the end. So think about, how are you disseminating this work to other people? Because that's where the reproducibility becomes the trickiest. What are the figures, numbers, things that they're going to look at? What is the supporting data that someone would need to reproduce those? And what's the best way of getting those materials to them? So it won't necessarily be like this GitHub repository. You're not going to put that data into a GitHub repository, right? But you do want to think about how can people access that data? Is there examples of people in my field who are using similar workflows that have solved some of these issues, and how have they done it? I think it's kind of an unsatisfying answer, but it's also probably the most appropriate that a lot of these best practices are, like I said, evolving in different fields. So see if there are people that are pushing the envelope in your fields and have found a way to share their databases, or a subset of their databases, or found some way of brokering access to them for someone who's interested in building upon their research, so that it's not always just a, take our word for it. So it's a spectrum, right? It's like, what can you share? You can share your code probably, right? And you can share some information about how to access your database. And whether or not it's possible for you to share maybe a subset of that to just illustrate the workflow for somebody else in more of a high-level way. Is that helpful?
Yeah.
Yeah. Do you know other people in your field that are following similar methods? No. See, that's one of the issues with reproducibility in general, right? Is because there's a lot of guidance out there that is very method specific because it has to be, and trying to figure out how that applies to your own work is a real challenge. But yeah, I mean, think of those things that just help you understand what you did in the future and share that documentation. You're still ahead of the game compared to a lot of other researchers out there. And share, when you find a solution for yourself, share it publicly so other people who are having the same challenge can, figure it out for themselves too. One really great piece of guidance for reproducibility is a Git book. It's free. It's in the slide deck. I believe it's in the slide deck. If not, I will add it there. It's called The Practice of Reproducible Research and includes case studies. So a lot of times you'll have this sort of like high level, you should centralize everything, you should share everything. And then when someone actually tries to apply that in their lab, it looks very different than what you might expect. So having those case studies can be really useful to see how someone who might have some of the similar problems that you have actually dealt with it in their own lab. So I would recommend checking that Git book to see if there's a case study that relates to the kind of work you're doing. Any other questions? Yeah.
Is it common to also include like a test directory in your master directory?
I think it's whether it's common or not, it's a good idea. Yeah.
Do you have any instructions on how to write a good test?
For a test for, so there's a really interesting group right now. I'm not sure if this is the type of test you're thinking about, but frictionless data is the initiative. They're part of the Open Knowledge Foundation. And one of the things that they've built is let me see, documentation, data packages. Let me find this. Good tables, I think, is. I thought it would actually take me to. Okay, yeah. So Good Tables is part of this frictionless data initiative, and they help simplify certain types of testing relating to data, where you have sort of an automated and ongoing verification that your data remains valid. And I'm not sure. I think the testing, as it comes to the actual like coding side, I think there's stuff coming up in this series relating to that specifically. I can't speak to it personally, but this type of validation of your data is really useful when you share it, because then somebody knows when they download the data and are trying to play around with it themselves, they can check that the data is the same that you have and that there's not missing values or that maybe something's got corrupted or something like that. So this makes that type of testing of your data very straightforward. They also are doing this cool thing, since we're talking about them, about data packages, which includes that validation. So you're actually, like, they call it packaging up your data, the way you package up your code, so that people can more easily get it running, get it going for themselves and use it for themselves. It includes that validation step. I'll add this to the slide deck so you guys can look at it later. Okay, so similarly, we want to be creating a data dictionary. So your data dictionary should accompany your data set. I call code books and data sets or data dictionaries the same thing. Some people argue with me about that, but you can call it a data dictionary if you prefer. It is a little bit more self-explanatory. But the essentials that you want in your data dictionary are, what are the variable names? So people can identify what, variables you're talking about in your data set. And what do they mean in a human understandable way? Where did this data come from? How does it relate to other bits of data? And things like natural thresholds, as I mentioned before. Business ascending, okay. So you can, again, always preview the changes that you're making with this left click show markdown preview. So the participant name is fairly straightforward. Trade number, see that would require some explanation because I just chose 0, 1, and 2, and that's not necessarily intuitive as to what a trade 0 might be. So explaining what that means so that somebody can look at that, they can look at your protocol, and they can understand the connection between that data and what you did in the room. I mentioned the importance of putting natural thresholds in. You have here in the happiness training a discussion of the scale and what the scale means. And then I put decimal ratings were allowed because one time people put in decimals and I hadn't explicitly said that they weren't allowed. So they're allowed, and then what type of values to expect in that element or variable of your data set. Any questions about data dictionaries? So if you go here, I have some of my favorite resources for creating data dictionaries. So you can see they can be quite rich depending on how complex your work is. And when you're publishing, you want to ensure that it's enough information for somebody to actually get started with reusing your data themselves. And this is actually, it refers here to the DMP tool. Who here has heard about a data management plan? No? So it's going to become an increasingly common request in grants for researchers to supply a DMP or data management plan, which is essentially just an outline of what data are you going to gather, where will it be stored, who will have access to it, what are you going to do with it in the long term, are you going to share it? So one of the key points that people will repeat when they talk about reproducibility is the importance of planning for reproducibility from the start. And I don't spend a lot of time talking about that here because I'm trying to focus on things that you can incorporate at any point in your workflow. But the best practice is to create a plan for reproducibility from the beginning. And that includes creating a plan for the life of your data and a plan for the life of your code and any other materials that you have. So this DMP tool, can look here. It's free, and the nice thing about it is that you can pick DMPs based on what funder you're most likely to be involved with, and that will structure things in a way that they expect. But essentially, what you're doing is creating a plan for how you will store, use, share your data, and by doing that at the beginning, you can be sure that any of those barriers you might meet at the end, especially if you're dealing with sensitive data, you've thought of from the beginning, which means you're more likely to be able to overcome them. So, for example, if you have sensitive data and you plan from the beginning to share some subset of that data, you can ensure that in your consent forms that you have acquired the appropriate consent to share some data at the end. That's a barrier that some people find at the end. They want to share their data, but it's not clear whether they've been given permission in advance by some of the other people involved. It also ensures that you're on the same page with your collaborators about what you're going to do with your data and your code. So the DMP tool, it's super easy to use. I think it might make me. I wonder if you guys are affiliated. No. Oh well. Yeah, so the DMP tool is a great way to get started thinking about this data sharing from the beginning. So the data dictionary examples here, these two are very academic and related to research. Carl Broman's is nice because all of his blog posts on reproducibility are short and sweet. So if you only have, say, a half a day to put something together, go to Carl Broman's blog first because he will give you the essentials. And then, building upon that, you can dive into some of the rich data management specialists and library resources, which often have very long, rich guidance, which is useful, but we're often having to take baby steps, right, towards these things. So start with Carl Roman. Any questions about the data dictionary stuff? Oh. You notice that I use the term exercise very loosely. Okay, so automation. The two things to keep in mind if you're just trying to get your research to be easily rerun by someone else is to use relative rather than absolute paths. And I'll talk about what that means in a minute. And then to create a master script that runs all of your analyses in sequence from start to finish. And any of the things that you might manually be doing to, say, your data sets or your scripts, and these are anything that you do manually is a barrier to reproducibility unless you create very rich documentation explaining exactly how somebody can manually replicate what you did. So scripting those parts of your data analysis as much as possible helps aid in the reproducibility. It also helps you to remember what you did because you actually have that in script format. And if you're doing that type of, say, data processing or data cleaning to multiple files, you can have a master script actually do that for you, so you can have it run on multiple files at once in one file. I'll show you what I mean because that's a little bit confusing. But essentially, it's one script to rule them all, and for complex analyses, it can be really essential for other people to understand what you did. So again, I swear Carl Rowan, I don't even know him, but I talk about him a lot in my talks. He talks about the importance of relative paths in his blog post. Essentially, what he means is if there is a path that leads to a place on your local computer or whatever system you're using that doesn't exist on the system that your reuser is using, that's a barrier to reproducibility. And they're going to have to dive into your code and try and manually update each one of those paths. But if you use what are called relative paths, in this case, he's got, he's telling the computer to go up one directory, look for the raw data subdirectory, and look for a file by this name. That's a relative path. So if somebody downloads your repository and they've retained your subdirectory structure that we've created, so you have your code somewhere, in this case he's got raw data as a folder, then your script will actually still be able to find all of those materials without people having to try and figure out why the code is breaking. Any questions about that? Okay. There's also, here we go. I mentioned the case studies resource. This is the resource I was talking about. This also has some great examples of master scripts and talking about the importance of creating a master script in here. But these case studies are a great place to start if you're trying to find examples in your field of people that are trying to adopt reproducible practices. So that includes some information on creating a master script. I know it was in there somewhere. So yeah, just to reiterate, this is one of the things that Woodbridge and his team found when they were trying to reproduce these Jupyter notebooks, is oftentimes there was some manual setup necessary to get them going. Files needed to be moved around, or some of the paths needed to be changed, or things needed to be in a certain order, and you had to do that by clicking and running them in order. So if you provide enough documentation for someone else to know how to reuse your data and how to rerun your code, then that's moving you down that spectrum. but oftentimes, especially if you're running the same type of research over and over again, you're going to want to automate as much of that as you can. Master script, saving our results explicitly and using relative paths is how we're going to do that. So the first thing we're going to do is create a master script to execute your code. Everybody still has their pink stickies up because I never took them down. So we're going to go back into our Jupyter lab here. Maybe. Oh, mine died. Did your guys die? No, here we go. Okay. So one of the things you can do with Jupyter Lab is you can create notebooks, you can create text files, you can create README documents, pretty much anything that you want. But you can also run a terminal. So what we're going to do is we're going to go to the code subdirectory. Anyone know how we do that? That's CD. So what I just did, because I did it quite quickly, I want to make sure everybody's on the same page. There's a thing called the launcher that you should have open in a tab. If you don't, you can click New Launcher, which is this plus here. And then you click Terminal. We'll close that old one, so we only have one. Okay? And then we're going to put in CD code. This just moves us to the code subdirectory that we created earlier, which is where our master script is currently located. Okay? So then when you hit enter, you should see this wavy line code. So when you see that, switch it to green sticky. Okay, so what is it that we're looking at in here? You click on the master script. This is a shell script. Your master script can be in R, it can be in Python, it can be in anything. It just is a bit of code that runs everything. In this particular one, it's saying first run this Python script, then run this Python script. So it's telling you what order to run things in, right? Then create a requirements.txt file in my results folder. So anyone who's looking at my results knows what the most up-to-date version of my dependencies, my packages, and their versions are. And then I have a Jupyter notebook, but I want to save it as an HTML so people can view it and execute it in a browser so they can actually read the whole analysis in the Jupyter notebook. So I've put that also in my my master script. So if we go back to this terminal, everyone put your pink sticky up again. We're going to run this master script. We're going to put dot /. You don't have to worry about the details of that. That's just because of the way the command line works. But you're going to put dot / run.sh. So this will only work if we've done all the work with the subdirectories and everything, because the code is reliant on that. Okay, and then once you have that dot / run.sh, we're going to run that master script. It's going to run all of our analyses against our data and save a requirements.txt file as well as our executed Jupyter notebook in the results folder. Okay, we hit enter, and if we're lucky, yep, we're converting our notebook to HTML. We're executing our notebook with Python 3. We're saving some things. Oh. So if you see that, switch your sticky to green. Is anyone having trouble with this one? Okay, there's a few people that don't have it. Are you good? No?
My notebook died, so.
Oh, yeah. So that does happen with Binder, unfortunately. So the pros and the cons. If you go back to the GitHub and try and relaunch it, you could dive into it again. But you can at least see up here how things are working. What about you? Did your notebook die as well?
No, I'm catching up.
Catching up? Cool. And you, sir, with the pink sticky? Is your notebook dead or?
Some error probably because my Python, I guess. I don't have Python 3 on my.
It should still work on. Oh, are you in the binder? Have you launched the binder?
Yes.
Yeah. So it shouldn't matter that because one of the benefits to using the container is that it shouldn't matter what you have loaded locally. So what error are you seeing?
I'm not found.
Okay. So I'll come to you in a minute after we check, make sure we're all on the same page with the results. Sound good? I don't want to leave anyone behind, but we can also just follow along up here. So now you'll see in your results file, we have, if we click on the Candy Trade HTML and open it in a new browser tab, now you see this is the executed Jupyter notebook. So all of the code has been executed, so you can see the output alongside the code and the narrative. And you can see that people get happier the more they trade their candy, which I suppose is expected. And we also have the images from the two Python scripts that we ran, and the requirements.txt file. So having this connection, keeping this connection to the results folder live means that I always know every time I run, this will be updated with the most recent requirements. And if I need to troubleshoot something, I know that this is related to the most recent version of my code and the most recent version of my table.
How do you render the HTML file in your notebook? Mine's just showing up as HTML code.
Yeah, so you have to right-click and then click Open in New Browser tab. Yeah, because it doesn't, for some reason, actually render HTML. They should, but they don't.
That code to work in the container or to work organize everything in that?
The container is best for sharing that step of it. There are tools now where you could, in theory, be developing your code and configuring the container in the background at the same time. None of those are perfect for every workflow yet, but I think Binder right now, for example, is really a great tool for, well, running workshops and just sharing your code with your colleagues at a particular point in time so they can dive around and get going with it. But you would probably be using GitHub for the actual collaborative code development. So when you have, so if you see here, if you configure, let me show you how I got this. Is that interesting to people? It wasn't part of the curriculum, but maybe it's interesting to you. If you go to my binder, my binder, I don't know if it's .com, mybinder.org. You simply put your GitHub repository in there. As long as it has an up-to-date requirements.txt file in it, it will just build automatically a container, and then you can, here I'll show you, so with mine. I don't know if doing this again might break the existing one, but we've just run it, so it's okay. You just put it in here, to master, and you just click launch. And when it's done, you can actually just embed this image in your GitHub repo in the README file. I don't know if you noticed in our
README file here. This top part is just that badge. So if you want to use this as part of a collaborative, like building a container as you are doing your work, this would be a good way to do it. So you have everything in a repo. The repo has to be public for Binder to work. You can install a local Binder instance if you want to, because it's open source. But you can just have that Launch Binder button in there. You just keep updating your code, and anyone who wants to just dive in and see how it runs and rerun it can just hit the button. And that will spin up a container. But you're not working in a container. Do you know what I mean? You just have to keep that requirements.txt file up to date. Okay. So we're at 11, 12. Okay, so we talked about absolute paths and relative paths. We have already, in this case, have all of our paths as relative. But one thing that I've seen people do, if you are going to make those changes, is you can actually, in the shell script, say that everything, all of your absolute paths in your scripts might all be the same, right? So you might have like a local, like desktop, it says in your code, like desktop/research/data or something like that. You can actually use a master script to have the script as it's running find every absolute path and change it to a relative path before you run your code. So if you find yourself coming to the end of a project and realize you just haven't been doing this the whole time and it would be really time consuming to update them all manually, that's one way that you can change those paths so that people don't have to go in and do it themselves. Okay, so when we talk about reproducibility, we do focus on the published literature. And that's because this is the main way that we as researchers communicate to one another the research that we're doing and what we found. But we're currently in a place where there are people that are attempting to share the materials that we need to actually allow for more reproducible work. But we're still quite far away from coming up with standards as to how to share those. And so I'm going to talk a little bit about some of the things to look for when you're choosing a way of sharing your methods and your code and your data alongside a published paper. I'll show you an example of a pathway that you could choose, say if you use GitHub, but the general things that you need to look for are whether or not you can specify an exact version of all your materials that relate to the state of your work at the time of publication. So it supports that paper so that people aren't coming back to a repository that is maybe 3 months or 4 months ahead of the publication that they're reading, for example. So you want to archive a version. You want to create what's called a persistent identifier for your repository. So a persistent identifier is just a public record of that particular repository that will be archived for people to be able to access, even if the repository itself, say if GitHub goes out of business or something like that, you still are able to access that information. And your identifier, which is essentially just a URL, will always remain the same and will always resolve to something. So people will always be able to find what they're looking for, no matter what happens to all the different tools and platforms that they're using. So we want to embed or link our code persistently. We want to obtain a DOI if possible. This is a type of persistent identifier that's appropriate for research materials. We want to cross-link our repository with our publication so that when someone discovers your code and data, they can go from that repository to the published paper. And also, if they find your paper first, they can go the other direction back to your repository. So that discoverability is less of an issue. There's also ways of actually embedding this work within repositories itself. Some of that is still ongoing. I know Dataverse is looking to integrate with some of these containerized platforms so that you can actually have the article with the code embedded inside of it, and you don't need to even leave that place to start to rerun it yourself. But the example I want to show you is, I think, a fairly versatile one where you can have all of your code, all of your materials, as much as possible in, for example, a GitHub repo that's public. Then you create a binder version of it. So that's, I showed you the intro of how to do that. You would create a badge that would actually run that requirements.txt file, spin up a container for someone else to use. And then you would take that GitHub repo and you would archive it in Zenodo. So Zenodo is free. It's a repository for research materials. Oops. And one of the reasons why I point people to Zenodo is because it's integrated with GitHub. So it's really easy to actually just create an archived version and a DOI for your GitHub repository that you can then share within your published article itself. So in my notes, did I put in an example of that? Yeah. Oh, it's making me sign in. Yeah, so I usually do this on my own laptop, and you're seeing how many times I've realized that that is the best way to do it. But if you go into the notes of the paper, you'll see an example. It's making me sign into Zenodo. Oh no, here we go. I lied. Okay, here's an example of a project that is in GitHub that has received a DOI for the one particular version of the project to support publication. So we published this open science training handbook. We developed it over GitHub, and then we minted this DOI. And we can continue to work on this project and within GitHub, and it traces that connection from the beginning to the end, and from the released version or say a published version to the most recent version. But you also always have this DOI will always resolve to this archived version of that work.
That DOI keeps the connection even if you keep working on it. The new version would require a new DOI or the existing one already traces?
So the best way to do it, and Zenodo allows this, is multiple versions of the same repository. So what you would do is mark important moments in your repository's life. So publications are obvious ones, but also any major update. So you could mint a DOI for the peer review process, and then you can share that with your reviewers, and then they'll give you feedback. You'll update it, then mint another DOI for the version that supports the actual published paper. And then if you continue to develop it, you would only mint a DOI for those important moments. It would link back to your GitHub repo. So here you can see that. This links back to the GitHub repo, but this has been updated since that DOI. So this is not the exact same version that Zenodo has archived, but it does give you that most up-to-date. Yeah.
It's frozen in time.
It's frozen in time, exactly. And that's intentional, right? Because we want to, release things quickly. We want information to get out there quickly. And if we're going to continue to do work on our work, this allows you to sort of do like micro releases, right? Micro publishing, getting out information as you create it. And then you can still keep working on projects and people will still be able to find the most recent version. Any other questions about that? Okay, so once you have centralized everything in a repository, you've got it to the point where you can use some sort of container technology to spin up a version of your of your analysis and your code. You want to specify a license. So the absolute easiest way to do this is if you're using GitHub. Again, I'm not signed in, so I'm not sure how this is going to work. Do you guys have GitHub locally? Okay. So I'm just going to tell you what to do, and you can tell me if you're running into issues with it. So go to a GitHub repo of your own. Okay. Now click on, I believe it's create a new file. Is that something you see? Okay. Click on create a new file and start to type in the name of that file. Start to type in license, L-I-C-E-N. And you'll see pop up on the right a little button that wasn't there before that says choose a license. Raise your hand if you see that. Some people don't see it. Okay. I'm supposed to see here.
Oh, you have to type it all the way.
Okay, yeah. Anyone still not seeing it? You're not seeing it? Okay. Sorry that I don't, not signed it to GitHub. I create a new file, and then start to type in license, and then choose a license template. So, so if you're using GitHub, they've made it really easy for you to use some of the out-of-box licenses. MIT is a common one for open source code, and for data, there's a lot of debate around what's an appropriate license. It's probably best to consult your library, but CC0, which is Creative Commons 0, also known as public domain, is appropriate for research data because it signals very strongly that you want people to use your data. You can choose Creative Commons attribution, which is CC BY, which is the same thing in terms of encouraging people to reuse your data, except that it requires attribution, so they have to cite you and give you credit for your data. One thing to keep in mind, though, is the norms in research, generally speaking, are that we cite each other's work when we use it. So if you use CC0, you're still going to get credit for that data. It's just not required. So it's definitely a choice. There's other options in that box of like having commercial restrictions on it, for example, if you don't want commercial entities to be reusing your data. Yeah.
Sort of a comment. I throw an MIT license on all my stuff, but I'm pretty sure Memorial Sloan Kettering owns everything, and their license trumps what we put.
It's interesting, actually. So every institution is very different. So Harvard recently, and I don't know what the most recent news about this is, they've decided to officially state that they own all of the data and code created by Harvard, and that they're going to openly license it, or something like that. I don't remember the second part of it, but they've recently decided to kind of clarify that because there's a lot of, it's a little bit confusing, I think, to figure out where your rights lie and where those lie of the institution. So the library is the best place to go to, or the tech transfer folks. But this is one of the advantages of writing a data management plan at the beginning, in your grant, because if your grant requires, if you put in a data management plan that says that you're going to share your code and data at the end, and then your grant says, okay, we will, as long as you follow this data, we will give you this money as long as you follow through the grant. That allows you to say, this is part of my grant mandate, that I need to share my data and code under this license, and it can help have that conversation happen. But obviously that's like good news too late for many people. The library is a good place to talk to about that sort of stuff. Yeah, but you're right. Like the norm is that people are just sharing it open source anyways, and they're not getting in trouble for it.
Yeah.
So it's an evolving space.
There's 1 out of 1,000 of those that's a blockbuster that some company will want, and then.
Yeah. Yeah, exactly. And I think as there are more mandates coming in the pipeline for not just the funders, but the institutions will have their own mandates. We're seeing that more and more, and we're also seeing journals now require that you share data to support an article or code to support an article. It's going to have to be that people have the ability to share that. So I think we're kind of in a transitionary time right now for a lot of those questions. Thank you. Okay. So in terms of picking licenses, I have a few guides here. But as he mentioned, and as I mentioned, the library is a good place to try and sort through what's appropriate for your work. Yeah, so make sure you share your code, share your data, and share enough of the documentation to allow someone else to get it going. One good test for this is to try and get someone else to rerun your code before you submit it to a paper to see what the gaps are in documentation. Someone that doesn't work with you in your lab, and that can really help to, work with the bugs and those gaps and those assumptions before having to deal with a slower process of a peer review version of it. Okay, so I'm finished early, which is what I was hoping would happen. Are there any questions about anything that we covered just started?
Could you go over the licensing options again?
Yeah.
The options that came up in the GitHub page, I couldn't follow along.
So the data licenses, for some reason that's not letting me. Digital curation sections. So this is a really great guide to picking a data license because they compare each license. There's standard licenses, there's Creative Commons. These are the different Creative Commons licenses. So there's CC BY, which requires attribution, share alike, which means that someone else that builds upon your data is required to license it with a license that is equally open to your license. So it's a way of ensuring that your data is not only open, but also everything built upon it remains open. No derivatives means no one can create a derivative work of your data, so it's quite restrictive. Non-commercial is it's sort of, I guess, in some ways intuitive that it means that commercial entities can't use your data. But one of the practicalities of this is that many academics are working in a space where some of their organization might be involved in commercial work and some of it might be involved in nonprofit work. So you might end up excluding some researchers from using your work, even if you might be interested in that type of work. That type of reuse. So this one is oftentimes not recommended, but it's your choice. So the nice thing about this resource is that it talks about what each license is good for and what are the downsides to it. So one of the problems with CC BY is what's called attribution stacking, which is where a commonly used data set that's CC BY will just end up with this huge, long, sort of unmanageable list of attributions for every single person that's built upon it. Which, you know, is, I guess, a good problem to have. There's an Open Data Commons license for data that's made specifically for research data or data. So it is appropriate for sure for data licensing. So I would recommend going through this for your data. And then there's also a choose license. At choosealicense.com. This is for your code. So it's actually like a little click-through algorithm. Tells you, based on how you answer these questions, what licenses are appropriate for your code. So if you are wanting it to be simple and permissive, you can click on that and it will recommend to you an MIT license, for example. Yeah.
How much legal clout does this actually have? Because it seems really easy to just arbitrarily pick one. So in the end, like if there's any sort of conflict, like, what does this license actually do?
Well, these licenses are very commonly used and therefore good ones to choose because the cases of like the gray areas have more sort of public guidance and conversation around them, so you'll have a clearer idea of what is appropriate use and what isn't. So that's one of the benefits of choosing these more common licenses like the MIT or the Creative Commons. In terms of legal clout, I mean, they're definitely legal documents. If you include a license.txt in your repository, that's like a legally binding like requirement for people to follow the license. But as I said before about the CC0 being appropriate for data because the norms around citation are so strong, I think there's not much you can really do, any of us as individuals, to ensure that we're going to get cited appropriately, or if we have, say we have a license that requires that all derivatives are openly licensed, you and I are not going to easily be able to check that that is followed through. And that's kind of where the norms like come into play, where we also need to, just as researchers, just say like, if you're using someone else's work, you've got to follow their license appropriately. And there's limits to how well we can enforce that. So, you know, you have to take those risks alongside with making your work public. You can signal strongly what's appropriate. You can assume that if the community finds that someone's not using your work appropriately, that they will hopefully call them out for that. But it is a risk that you're going to have to take. I think it's a risk worthwhile because you also will be surprised by the new uses of your work, your data and your code, if you share it really clearly as well. So, yeah, it is a bit of you are walking out into the trust of the community a little bit. In theory, you could, you know, if you saw someone misusing your work, there are avenues for trying to rectify that, right? Especially if it's published. Sometimes in the journal, if someone has published using your data and not cited it, not attributed it to you, that journal should be able to get in touch with them and rectify that. Any other questions? Any questions about reproducibility or open science in general?
What additional use you find from the container that the repository doesn't provide? It's the same documents, requirements and text.
So you'll notice that I was able to execute my Jupyter notebook, right? So like if you share a GitHub repo that has all this documentation in it that we talked about, then that's a reproducible repository, and it's totally appropriate, especially if you mint a DOI with it. But if you include a container technology of some sort, then it means someone can actually start to play around with your code without downloading anything themselves. So you'll notice that you guys were all able to play around with that notebook without installing anything. And that's nice, especially with a publication, because when you see a figure, you're like, oh, okay, but you had this threshold, right? Or you displayed your information in this particular way. What happens if I, sort the categories differently? Someone can just jump in and play around with that without installing anything. So it just speeds things up. It bridges the gap between like theoretical reproducibility from like practical reproducibility.
I feel that in my own research, I can only use GitHub for small data sets, but the file sizes get big.
Yeah.
Easily usable anymore.
No, and I mean, you can still configure a Docker container with your analyses and have the data be just a reference to the data so that people can access it in a way that makes sense. And that still allows them to get the code running more quickly. But yeah, sometimes your data and your code just can't be in the same place, and that's just the world. That's the way it works sometimes. All right, great. Yep.
So if I found a Jupyter notebook on GitHub, how do I actually run it?
Yeah, so that's a good question. So you can start by just trying to run it locally and see if it works. And if it doesn't work for you, you're going to have to do a little bit of archaeology. If you have just the notebook, you're going to have to read it, see what packages are necessary, install the most recent versions of those packages. If those packages will have their own dependencies.
So it's not totally self-contained that I can just click somewhere and run the analysis.
Exactly. That's the problem, right? That's the crux of the problem, is that there are still dependencies. And so when you're trying to troubleshoot other people's dependencies, install the most recent version, see if it works. If it doesn't, then you can start to go back to previous versions and see if maybe they use previous version. But this is what they term dependency help. It's when you're trying to figure out those dependencies. And oftentimes, it can take a lot of back and forth with the author to figure out what they did, which is time consuming. And sometimes it's not even possible. Like, they don't know why it's not running, you don't know why it's not running. Something's missing, and it wasn't documented. And so what a lot of people do is they might have the best intention of reusing someone's data and code, but when it's so much work to get it going, that they think, well, if I create my own data and code, I know I'll eventually get there. I don't know, there's a question mark as to whether I can ever get this running, then people will drop it. And that's, even though you might be theoretically creating reproducible work, in theory, people are actually not able to build upon it. So that's what we're hoping to bridge that gap with practical reproducibility. Any other questions? Cool. All right, well, I'm going to be here till noon. So if you do have questions, just stick around. Take all the candy with you, please. And thanks so much for coming. Let the organizers know what you liked and didn't like about this session. If there's things you'd like to see, if we ran it again in the future, let me know, because I always update the curriculum based on what people's feedback is. So thanks so much. Thanks for your questions and your participation. Have a good day.